Hi guys, this video will help you prepare for the Prerequisite Algebra Skills exam. It's your first exam and it's going to test you on all the algebra skills that I think you need to be successful in this course. The first two problems are very similar, you can see. One is a square root and one is a cube root. Really there's an invisible 2 here for the square root, but we use those so much that we just kind of got lazy and dropped that 2. But I do have the same number here, 320. So let's look at the difference between square roots and cube roots. The goal here, we're trying to put it in reduced radical form, which means you're going to take whatever square root you can from perfect squares, or take the cube root that you can from perfect cubes. All right, let's look at that number 320, and your goal is to just break it down and find perfect squares. I can immediately see that 320 is 10 times 32, 10 is 2 times 5, 32 is 2 times 16, and just keep going. 2 times 8, 2 times 4, and 4 is 2 times 2. So what did I do? I just wrote all this 320 basically as the product of all of these prime numbers. And why am I doing that? I'm trying to look for perfect squares. So I see one right here. 2 times 2 is 4. I see another right here, 4. And then I have this 4, 2 times 2. So let's just rewrite this radical here. 320 is the same thing as 4 times 4 times 4 times 5. Don't forget about your 5 here. And let's break down the variables now. X to the 4th is x times x times x times x, or x squared times x squared. And both of those would be perfect squares. And finally, y cubed is y times y times y. And you can see here that this is a perfect square, y squared. And then you've got that last y. So now we've basically rewritten everything under this radical, broken down into the perfect squares that we can find. And now that we've found them, we can actually take the square root. So I'm going to go ahead and do that. The square root of this first 4 is 2, so I'm going to take that 2 out. Square root of 4 is 2, so it's gone. The square root of this 4 is 2, so I'm going to take that 2 out. And these are all multiplying each other. Likewise, this last 4. Now that 5 is not a perfect square, so it's going to remain under that radical, and we can't take that out. The square root of x squared is x. The square root of the next x squared is another x. The square root of y squared is y. And we cannot take again this square root of just this last y because it's not a perfect square. So I'm going to take that out. And what do we have left? In the radical we have 5y. And now let's just button everything up. So 2 times 2 times 2 is 8. X times x is x squared, and then we've got that y, and finally 5y. So this is our reduced radical format. Now let's go ahead and take a look at what it looks like to take a cube root. We're looking for perfect cubes now instead of perfect squares. And it's convenient that I chose the same number here, so let's rewrite 320 again as 4 times 4 times 4 times 5. Now let's look at perfect cubes. S to the 4th is s times s times s times s. And there's a perfect cube, s cubed times s. So I'm going to go ahead and write that as s cubed times s up here. And then x squared is not a cube. We can not break that down into 3, so I'm just going to leave that alone. All right, now where's the cube? Well, here it is. There's essentially the number 64. And by the way, I just noticed I forgot my cube root here. So the cube root of 4 to the 3rd, remember, we're looking for inverse operations. So if I have 4 cubed, if I wanted to take the cube root of that, that's the inverse operation. That just gets me right back to 4. So that's what we're doing here. Cube root of 64, or 4 times 4 times 4, is 4. So I'm going to go ahead and take that out. The cube root of 5, well, 5 is not a perfect cube, so that's going to be stuck. The cube root of s cubed is s. So I'm going to take that out. And just this single s here and x squared, neither one of these are perfect cubes, so I can't take those out. So what do I have left? I have my radical, and I have my cube root here. 5 is stuck under there, s is stuck under there, and x squared is stuck under there. So I have just reduced out everything I can. Okay, problem number 3 and problem number 4 are similar to these types of problems. Here we're looking for a cube root again, so we want to break down that 343 into cubes. And I don't know really what that's divisible by. So I look at this number and I say, okay, it's an odd number. I can't divide it by 2. Now I'm going to sum up these digits here. 3 plus 4 is 7, plus 3 is 10. It's not divisible by 3. And so I'm a little bit confused. I might want to get out my calculator at this point. Or I guess I could start looking at cubes. So I know 2 times 2 times 2 equals 8. 3 times 3 times 3 is 9 times 3, which is 27. So right now I'm just kind of practicing or trial and error here. We know this is 64. 5 times 5 times 5 equals 125. 6 times 6 times 6. Well, let's look at that. That is 36 times 6. And that turns out to be 216. And so I'm just getting closer and closer here and seeing what I can find. This is just pure trial and error. 7 times 7 times 7 is 49 times 7. And if you do that long multiplication out or use a calculator, you will see that that is indeed 343. So I'm taking the cube root of 7 times 7 times 7. Well, that's the cube root of 7 cubed. And the cube root is the inverse operation of cubing. And so I know that this just simplifies to 7. Okay, number 4. Let's try to reduce in radical format. This is a square root, since there's no number there. And we just try to break down 80. So 80 is, let's say, 4 times 20. Let's break it down. 2 times 2, and 20 is 2 times 10, and 10 is 2 times 5. So where's our squares? Well, we've got one right here, and we've got another. Let's rewrite our problem. We've got 80 is the same thing as, I'm going to erase that there, is the same thing as 4 times 4 times 5. X I'm going to leave alone. And y to the 4th, I've got 4 of these y's multiplying together, which is the same thing as y squared times y squared. Those are perfect squares. So now let's start taking the square root. We've got the square root of 4 is, this 4 is 2. I'm going to pull it out. We're done with it. Square root of this 4 is another 2. We're done. And you know what? I didn't leave myself much room here, so I'm going to move that. And the square root of 5, well, that's not a perfect square, so I got to stick that, keep that onto the radical. Likewise with this x. And the square root of y squared is just y, so I'm going to take that out. And the square root of the second y squared is y, so I'm going to take that out. And when we zip it all back together, we have 4y squared times the square root of 5x, and that is in perfect reduced radical format. Problem number 5 and problem number 6. Well, just a reminder that the square root of, the square and square root are inverse operations of each other. So if I had any number, x squared, and I'm going to take the square root of it, I'm going to get back x. If I have any square root of x, or any number, and I'm going to then square it, I'm going to get back x. It's yin and yang. They undo each other. They are inverse operations of each other. So here, if I have a square root, squaring of a square root, then all I'm going to end up with is whatever I started from. In this case, it was 8 5/10. They're inverse operations of each other, so they just undo each other. Okay, problem number 6. Simplify this cube root if you can. And as soon as I see this problem, I notice that I have a little typo. I really meant this problem to be the cube root of 297 minus 9 squared. So let's just cross that out. Okay, so let's take a look at this. Now, what we don't want to do is start breaking down these numbers individually. We can't do that since they're not a product. Okay, we can start breaking things down like we've done on the previous problems into prime factorization if we had a product, meaning many things being multiplied together. But in this case, we have a numerical expression that includes subtraction. So in a way, this expression here, this radical is acting like a grouping. So if we look at Pemdas, as you know, I've told you that the radicals are here at the exponent level, but this radical, in a way, is kind of up here in the parentheses because there's an expression underneath it. We need to work in there and simplify first before we start breaking down numbers. So let's take a look at 297. Let's simplify a little bit here. We've got the cube root of 297 minus, and we're going to take the square of 9. Now notice I didn't turn this into a plus 81. This subtraction here is not at all part of that exponent. So don't be fooled here. Don't turn this into an addition of 81. That is really just squaring the number 9. All right, so let's take a look at 297 minus 81. 7 minus 1 is 6. 9 minus 8 is 1. And we have 216. So let's rewrite this as the cube root of 216. Now we can start breaking that 216 down and see what we see. Let's see. I'm just going to go ahead and divide by 2, I guess. So we've got 2 times 108. 2 times 54. 54, I see, I guess 9 times 6. And 9 is 3 times 3. And that 6 is 2 times 3. Okay, so let's pair up. I've got 3 2s, 1, 2, 3, and I've got 3 3s. So up here I think I'm going to just say 2 times 3, 2 times 3, 2 times 3. So you can see I've got 6 times 6 times 6. And that's the perfect cube we're looking for right there. 6 times 6 times 6. And that's the cube root of 6 cubed. And the cube root undoes the cube, so we end up right back where we started from. And the answer is 6. Okay, number 7 and number 8. First, number 7, solve for C. Put your answer in reduced radical form. So here again, we're subtracting 4 squared. This is not, I'm going to do it incorrectly first. So I'm going to say not the same here. C squared, this does not turn into plus 16. Okay, so make sure that you are not making that mistake. That subtraction sign here, right here, is an operation. And that is not going to get captured into that square. So we've got to simplify first. C squared minus 16. I'm just taking the square of 4. And 8 squared is 64. Go to the unknown. Go directly to the unknown. Undo what's around it. So I'm going to undo subtraction with addition. Whatever I do on one side, I got to do on the other. I end up with C squared equals 80. And C squared equals 80. But what does C equal? Well, you got to undo that square with a square root. It's inverse operation. So we end up with C equals the square root of 80. And that is the answer, but I asked for the answer to be put in reduced radical form. So again, we're just going to break down 80 and try to find perfect squares. We've got 2 times 40, and 40 is 2 times 20, we can just keep going. 2 times 10, and 10 is 2 times 5. So we've got C equals, let's find those perfect squares. There's 1, there's a 4, here's another. So let's write that as 4 times 4 times 5. And we've got our perfect squares here, so take them out. C equals, the square root of 4 is 2, so I'm going to bring that out. The square root of 4 is 2, bring it out. And the square root of 5 is an imperfect square there, so we have to leave that in. And just simplify. 2 times 2 is 4. So we've got 4 times the square root of 5, or we say just 4 square roots of 5. So that's our answer. Okay, over here, solve for x. This is a proportion. Proportions, what is a proportion? A proportion is when we have an equality of ratios. So equal ratios. And many of you have heard about cross multiplication. But let's just quick review why that works. 5 halves equals 9 over x. 9 is being divided by x. How do you undo division? With multiplication. So if I multiply one side by x, I got to multiply the other side by x. Now over here on the left side, 5 is being divided by 2. How do you undo division of 2? We multiply by 2. Whatever I do on one side, I do on the other. Now here's what happens with this cross multiplication. 2 divided by itself reduces to 1, and x divided by itself reduces to 1. So it looks like this 2 here on the bottom just magically moved up and over that equal sign to multiply 9 over here, the numerator. Likewise, the x just magically moved up here. And that's where cross multiplication comes from. It really is just inverse operations at work. So I'm just going to get this out of my way. After you see this being the case, you can just cross multiply, and as long as you know where that comes from. So cross multiplication, you're always doing that across an equal sign. So 5 times x is 5x. 2 times 9 is 9. I'm sorry, 2 times 9 is 18. And we go to the unknown, go directly to the unknown, undo that multiplication with division, and your answer is x equals 18/5. You could reduce that if you wanted to, if you could, if it's possible. In this case, it's not. So this is a perfectly acceptable answer. I have no problem with improper fractions. Or you can maybe do a mixed fraction. 5 goes into 18 5 times with a remainder of 3. And you could also put this into a decimal here. We could say x equals 5, and 3/5 is the same thing as 6/10. So any one of these combinations I'm absolutely fine with. Okay, questions 9 and 10. These seem to baffle a lot of students, and I'm not totally sure why, but what we're trying to do here is find the value of this, solve for y, and y here is an exponent, and some of you are not seeing that. Maybe it's just not up high enough. But this is not 3y, this is 3 to the power of y. And so what we're trying to do is get the base to be the same, and it looks like it is the same here, 3. If we have 3 to the y, if I can get the other side with the same base, 3, and figure out what that exponent is up there, then y will be that exponent. Y would equal that exponent. Just get the bases the same. So let's use our understanding of exponents. This is 3 to the 4th as a base, and it's being squared. So I actually have 3 to the 4th times itself, right? Because we want to use the base times itself, the number of times that that exponent tells us. So that equals 3 to the y. And 3 to the 4th is 4 3's being multiplied by itself. And then over here, we've got the same thing. So count up the 3's. We've got a total of 8 3's multiplying itself, therefore y equals 8. So just don't try to memorize any rules. I mean, if you get to this point and you see, oh yeah, I'm supposed to multiply the exponents for power on power, it's called. Fair enough, but sometimes we add the exponents and a lot of students get confused with the rules. So I'm not a big fan of memorizing. I'm a fan of just understanding what a base and an exponent does and then just piecing it together. Okay, number 10. Here I did something a little sneaky, Anya, and I changed the base here. So you've got 2 and you got 2 here, but here's a 4. So we need to find a way to rewrite the number 4 using a base of 2. And hopefully you can see that 4 is the same thing as 2 raised to the power of 2 or 2 squared. So I'm going to rewrite that. I've got 2 cubed times, well, 4 is 2 squared, and that whole thing is being raised to the power of 8. And I've got this 2 to the x over here. So use your knowledge of exponents. 2 cubed is 2 times 2 times 2. That's 2 cubed. And over here I have 2 squared being multiplied by itself 8 times. I might as well write it. I mean, there's no harm in, I always say, when in doubt, write it out. So we have 2, 2, 1, 2, 3, 4, 5, 6, 7, 8. And this is one big product. They're all multiplying each other. So I've got 3 2's here. And I've got 2, 4, 6, 8, 10, 12, 14, 16. Again, power on power, multiply. So I've got 16 2's here. How many 2's are multiplying each other? I've got 19 total 2's. And therefore, I've got the same base here, and these exponents must be the same. So it's called 1 to 1. And x must equal 19. When in doubt, write it out. And do I have any? No. Number 11 is a factoring problem. So as soon as you see a square here, that's got to jog your memory that it's a quadratic. And as you've seen in my other videos, not all quadratics are factorable, but many are, and it's a very, very good skill to learn. And again, we always want to get everything on one side. Ax squared plus bx plus c equals 0. We always want to get everything on one side lined up in descending order of exponents. So let's take a look at that. We are now going to get everything over, so I'm going to subtract 13x and I'm going to subtract 12. Whatever I do on one side, I got to do on the other. So I'm just going to, well, this is a little messy. I don't like it to look this messy. 2x squared and 8x minus 13x is negative 5x. And there was no other constant over here for the 12 to combine with, so it's just minus 12. All right, fair enough. Now let's try to use that box method that I did on another video. We know that this first term here, 2x squared, goes right in that box, and c goes right in that box. So our task is to try to figure out what two terms here combine to give us that negative 5x. And the way we do that is we take a and c and we multiply them together. In this case, you've got to grab that sign. So 2 and a negative 12 is negative 24. So we're looking for factors of negative 24 that sum to this coefficient here, negative 5. And you could go through several iterations of coming up with factors of negative 24. There are many, but hopefully you see right away that a negative 8 and a positive 3 are going to sum to that negative 5. So we are going to go ahead and put those, we're going to use these numbers here as coefficients. And doesn't matter which box you put them in, but I'm going to rewrite negative 5x up here as the sum of negative 8x plus 3x. And we're basically just now going in reverse. Instead of multiplying binomials together, we're dividing out the factors. So go row by row and column by column. And I'm going to start with the first row here. What can we divide out of both terms, 2x squared and negative 8x, evenly? and that happens to be a 2 and an x. Now I'm going to look at this next row. What can be divided out of both of these terms, 3x and negative 12, and that's a positive 3. And now looking at column 1, what could be divided out of 2x squared and 3x? Only an x. And finally, what can be divided out of negative 8x and a negative 12, and that would be a negative 4. Now, if you have any questions about what sign should I be using here, just go back and mentally do your multiplication. Negative 4 times a positive 3 gives us that negative 12 we're looking for. Positive 2x times that negative 4 gives us this negative 8x that we're looking for, etc. So you can just kind of check your work right here with the box. So we've got the two factors now, x minus 4 and 2x plus 3, what we ended up with on the outside. And that equals 0, because basically we just replaced this quadratic with its factors. And that's kind of like rewriting 30 as the product of 5 and 6 type of thing. Once we have the factors, we can set them equal to 0 independently, and then solve for x. X equals positive 4, and 2x equals negative 3 if I subtract 3 from both sides, and x equals negative 3 halves if I divide both sides by 2. So there are two solutions, and with any quadratic, with a highest degree here, or highest exponent of 2, you could have up to 2 solutions. You could have 1, or you could have no solutions. Okay, moving on. Question 12. We see here we've got some kind of equation. We want to solve for x, but x is stuck here underneath the radical. So what are we going to do? Well, same thing we do on all equations. We're going to undo everything around that unknown x, and we're going to undo them with the inverse operations. And it's most convenient to apply those inverse operations by working from the bottom of Pemdas up. Okay, so why do we do that? Well, when we smush everything together, we work top down. And when we're pulling everything apart or everything off of that unknown, we're going to go in the reverse order. So what do we have in our problem? If we go to our unknown here, x, it's got a radical around it. And I told you in class that radical is really an exponent. In this case, since it's a square root, it's an exponent of 1/2. Now sometimes, if there are a lot of things going on inside that radical, as we've already seen, sometimes that's like a grouping up here, so you want to simplify, but in this case, it's that unknown is by itself. We also have multiplication. 3 is multiplying the radical, so that's this level. And we also have addition of 4, so that's this level. So working from the bottom up, we're going to undo that addition of 4 first. 4 minus itself reduces out to 0, and 31 minus 4 is 27. So we've taken care of that level. Now we're going to undo our multiplication. Oops, I see a little mistake I just did. And we undo multiplication with division. So I'm going to divide out that 3. And I end up with that reducing to 1, so I have square root of x equals 9. And we've taken care of that level. And now how do we undo a square root? Well, we undo a square root with square. So I'm going to square, let me do that in red, square that. And if I do that on one side, I got to do it on the other. So a square of a square root undoes each other. They're yin and yang, so they go away, and we end up with x equals 81. And if you want to check your work there, you can always just substitute back in. The square root of 81 is 9. 9 times 3 is 27, and 27 plus 4 does equal 31, so it's pretty easy to check your work. Okay, question 13 is another quadratic, and I am going to get everything on one side, so I'm going to subtract 2x from both sides. I end up with 3x squared plus 22x plus 20 equals negative 4. And again, I want that to be 0, so I've got to undo that with add 4. And I end up with 3x squared plus 22x plus 24 equals 0. At this point, if we can evenly divide anything out of all terms, we would definitely do that. We can't here, but we would do it if we could. So we have our 3x squared going in the first box, and we have our 24 going here. And we've got to multiply these together. So what do we end up with? We end up with 12, carry the 1, and we've got 72, I guess. And it's positive. So we're looking for factors of positive 72 that sum to 22. So the first thing that comes to my mind anyway for 72 would be 9 times 8. And that doesn't give us the 22. So 9 times 8, or 9 plus 8 is 17. So we're actually looking for a bigger number here than 17. So maybe if it's not readily apparent to you, break down one or two of these numbers. We could break down that 8 and see that 8 is 4 times 2. So maybe try these factors here. 9 times 2 is 18, so multiplied by 4 would give you 72. So try that out. We've got 18 and 4, and that also gives us 72, and that is adding up to what we're looking for. So we can use 18x and 4x, the sum of those, to represent our 22x here, and go ahead and start factoring row by row, column by column. So in the first row, I can take out a 3 and an x. Second row, a 4. First column, only an x. And the second column, I guess I could take out a 6. So we've got 3x plus 4 and x plus 6 equals 0. And we could put both of these equal to 0 independently. 3x plus 4 equals 0, x plus 6 equals 0. X is then going to equal negative 6, so that's going to be one of our solutions. And x is going to equal negative 4/3 is going to be our other solution. Okay, system of equations. I know many of you would use substitution, and maybe that would be something I might do too, because this equation right here is pretty simple. If I add y to both sides, then y is just a single term here. So maybe that would be an approach I might use. But I'm trying to get you, or encourage you to use elimination. So what do we want to do? We want to transform one or both of these in such a way that we can add them together and have one of the unknowns fall out. Now, one of the things I've seen a lot of, and I'm not at all clear where this is coming from, is when I see students all day long with a system of equations taking turns making the x a 0 and the y a 0. I have no idea. The only thing I can think of where that might come from is maybe students are confusing, trying to find x or y intercepts. That's my only thought, but that is not solving at all a system of equations. A system of equations is when we have two equations, well, could be n number of equations with n number of unknowns. In this case, we have two equations, 1, 2, and two unknowns, an x and a y. And so what we're looking for is a single value of x and a single value of y that satisfies both of these equations. And when I say satisfy, I mean when you substitute it back in, not it, but they back in, you end up with true statements, true equality. Okay, so let's look at transforming. Right here, the first thing I see, if we wanted to knock out the x term, I guess we could multiply both of these equations by numbers, where we would end up with a result here that they can subtract out from each other or cancel. The easiest thing I guess we could do is multiply this one by 6 and this one by 9, and then we would end up with negative 54x and this positive 54x, and that would go ahead and cancel that. Maybe it's easier here to look at the y terms. This one is positive 4y and this is just negative y. So hopefully you could see that if we multiply this by a positive 4, we would end up with this negative 4y that we're looking for. And when we multiply that by positive 4, we're multiplying every term by that positive 4. So we end up with 24x minus 4y, and we would also multiply that final term on the other side of the equal sign. It just happens to be 0, which is going to remain 0. But if that were a number, you would multiply it by 4. Okay, so now we have 24x. I'm going to line this up so that I can easily add like terms. Negative 9x plus 24x. What is that? We end up with a positive 15x. 4y minus y cancels to 0, reduces to 0. That's why we did it. And negative 5 plus 0 is negative 5. Go to the unknown, undo what's around it. So I'm going to undo that multiplication with division. And I end up with x equals negative 5/15 or negative 1/3. That's one of my solutions. Another thing I see a lot of students do is just solve for one unknown when we're supposed to be solving for both x and y. See, now that we know x, we would substitute that value of x into either one of these equations, and it really doesn't matter which one. It does seem like this equation here is the easiest, though. So I'm going to go ahead and substitute negative 1/3 in for x and solve for y. 6 times a negative 1/3, I have negative 2 minus y equals 0. I'm actually going to solve for y here by adding y to both sides, and I end up with negative 2 equals y. So that would be our second solution. If we were to substitute both of these values in both of these equations, we would end up with true equality statements up here. And that's the definition of system of equations. Okay, problem 15, 16, and 17 I put on the same page because they are all related, and I find these to be confusing for students. So what we have here are repeated addition. So let's just take something simple for a second. What if I had 4 plus 4 plus 4? That's repeated addition of the same number, and we know that we can rewrite that as multiplication. That would be 3 4s, or 3 times 4. Well, this is no different here in this problem. X plus x is repeated addition. We really have 1x plus 1x, and that's 2x. Now what I see students do, though, is they see that x and they say 2x squared, or maybe even just x squared. So that tells me they have some confusion about exponents and combining like terms. Combining like terms is really using the distributive property. So let's go ahead and use the distributive property in reverse and divide each of these terms by the greatest common divisor. Now what are they both divisible by? Well, I could take an x out of each of them. So if I divide x by x, I end up with 1. If I divide x by x again, I end up with 1. So I have x times 2, and by convention we just put that coefficient in the front. Well, that's the same exact thing we're doing here with this 4 plus 4 plus 4. Using the distributive property in reverse, I end up with 4 times 1 plus 1 plus 1, or 3. So combining like terms, whether it be constants or variables, it's rooted in the distributive property. Now, the student who mistakenly does this, x plus x equals x squared, that student is confusing combining like terms with multiplication, or the resulting product. So obviously x plus x does not equal x squared, and I could always, if I'm a person and I know that I have this weakness, I know that sometimes I get confused on these rules, then I would just take out the abstraction of variables and I would just put in a number. If I said x was something simple like 1 plus 1, is 1 plus 1 1 squared. No, 1 plus 1 equals 2, so it does not equal 1 squared or 1. So just kind of make yourself some little problems to just test out your thinking. And that way you know you will not get confused on the difference between multiplying or summing. So here again, on this problem 16, we've got repeated addition. 1x squared plus 1x squared is 2x squared. There are 2x squared. And again, we can do the same exercise here with the distributive property in reverse to combine those like terms. Now, I just encourage you that if you are this person who gets confused and you want to look at this and you want to say 2x to the 4th, or you want to say, let's say x to the 4th, try these things out. I'm going to put these question marks. Try them out with a number. Let's just make an example here. Let's say x equals 3, for example. Well, I have 3 squared plus 3 squared, and that's 9 plus 9, so that's 18. So I could easily substitute this, my number here, into here, and I can see 3 squared is 9 times 2 is 18. So that's a good way for me to just kind of say, kind of get myself situated and make sure that I have this right. As soon as you substitute in 3 over here, for this, for example, 3 times 3 times 3 would be 20, let's see, 27 times 3. Let me do that on my calculator. 27 times 3, that would be 81. So over here, 2 times 3 to the 4th is 2 times 81. And 2 times 81 certainly is not 18. It turns out to be 162. So this is just an easy approach to check your thinking. Don't take this for granted. They look like such simple little problems, but you'd be surprised at how many students get this confused. All right, last problem is same thing. Do not be at all confused by these square roots. This is repeated addition. Repeated addition. So again, using the distributive property, what are both terms evenly divisible by? They're evenly divisible by itself. So if I use the distributive property in reverse, I would end up here with square root of 3 times the sum of 1 and 1. And I can simplify this here to say that's the square root of 3 times 2, and by convention, we just put that number in front almost as if the square root of 3 were acting like a variable. So 1 square root of 3 plus 1 square root of 3 is 2 square roots of 3. Now, what a lot of students see here is they start doing things like this. This type of thing. So square root of 3 plus square root of 3 is the square root of 9. No, the square root of 9 is 3. And that certainly does not equal the square root of 3 plus square root of 3. So just take it for a test drive. Another great approach would be trying to make up your own problem here with perfect squares. So square root of 4 plus square root of 4. I know that's 2 plus 2, which equals 4. And I certainly know that that 4 does not equal the square root of 8. So that's another quick way that you can kind of check your reasoning. Finally here, linear functions. This is going to be, we are going to be using these skills the entire year on almost every topic that we take a look at. So it's critically important that you have very, very solid conceptual understanding of linear functions on the XY coordinate plane. Okay, so we've got some directions here. Graph the line between point A at negative 1, positive 3, which is right there, and 3, negative 2, which is right there. So I don't have a ruler, so I'm just going to sketch my line. It's not really great. But here's my line. What is the slope of this line? Well, slope M for mountain slope equals the rise over the run. And in this case, I want you to think left to right. If you're walking up a hill left to right, then we've got a positive slope. If you're walking downhill, left to right, then you have a negative slope. So in this case, we can sort of draw a triangle around here, and we can just count the boxes. 1, 2, 3, 4, 5. We've got a slope of -5 because we're going downhill. And our run is 1, 2, 3, 4. So we've got a run of 4. So our slope for this line is -5/4. C, my directions is calculate. Do not estimate the y-intercept of the line. So most of us know here that the y-intercept is where that linear function crosses the y-axis. And I don't want you to read it off the graph. So the y-axis, everywhere on that y-axis, x here, x is 0. Everywhere along here, x is not positive, x is not negative. Everywhere on that line, x equals 0. So when we look at the standard y equals mx plus b, which is the standard form slope y-intercept form of a line, the reason why this is the standard and that this is the y-intercept here is because if x equals 0, this term just drops out. Alright, so let's just write what we know. We know y equals -5/4, that's the slope, x plus b. Now, how do I solve for this b here? Well, we have two points here that we know are on our line. And the first number that's listed is x and the second is y. I can choose either one of these points. It does not matter which one. Both will work. And I'm just going to substitute in a value here for y and a value in here for x. So I've got a -1. By the way, this is negative. It just looks a little funny. So I've got 3 equals, a negative times a negative is a positive, plus b. So b is going to equal 3 minus 5/4. How do I simplify that? 3 minus, I'm going to go ahead and erase, I guess I can't. I'm going to represent 3 wholes in fourths. So b equals 12 fourths, which is the same thing as the number 3, minus 5/4. And 12 minus 5 is 7. So I've got a y-intercept of 7/4. I made a little mistake here. 7/4, positive. 7/4 is less than 2, but greater than 1. So it's 1 and a remainder of 3. So 1 3/4. You can see up here from my sketch, it's not very good because my line appears to be greater than that. All right, write the equation in slope y-intercept form. Well, now we're going to bring it all together. We've got y equals -5/4. That's our slope, x, plus b, which would be our y-intercept, and we just solved that to be 7/4. So that's the equation of our line. Now calculate. Do not estimate the the x-intercept. The x-intercept is where we're crossing the x-axis. Everywhere along this x-axis, everywhere along that x-axis, y is not positive, y is not negative, y is 0 on that line. So that's how we're going to calculate it. We've got our equation, and we're going to substitute y equals 0 and solve for x. That's going to be our x-intercept. So we've got our unknown here, and we want to get rid of this addition first by subtracting 7/4. We're going to end up with 7/4 over here, and we've got -5/4 x here. Now I'm going to divide, you know what, the easiest thing, I teach this to my algebra kids, just get rid of this 4. Nobody wants to deal with these fractions, so multiply everything by 4. Over here, 4 divided by itself reduces to 1. Over here, 4 divided by itself reduces to 1, so you end up with -5x. That's the easiest way to solve this. And divide out both sides by -5. And we end up with x equals negative divided by a negative is a positive. And that's the same thing as 1 2/5, which you can read as 1 4/10. So if we go back up here, well, yeah, my sketch is still off, but 1 4/10 is just shy of 1 1/2 or 1 5/10, so it's not too bad. Okay, so hopefully this video helps everyone prepare for their test, and have a great day.